morning, students. In earlier classes, we have discussed about the inverse Laplace transformations, various properties of inverse Laplace transformation, illustrative problems of the inverse Laplace transformations, and many more. Now we will discuss a very important property of the Laplace transformation, which is known as the convolution property or convolution theorem for the Laplace transformation. Before this theorem or this property, we will discuss about the convolution of two functions. So first, convolution of functions. Convolution of two functions f and z. So what is the convolution of two functions? So first we define the convolution of the two functions. The convolution of two functions fx and gx is defined by f star z, denoted by f star z. So f star z is the convolution of two functions, and the convolution of two functions is denoted by integral 0 to x f of x minus u z of u d. F of integral 0 to x f of x minus u z of u du, or we can also write it as integral 0 to x f of u z of x minus u d. So the convolution of two functions f and z is denoted by f star z, and it is given by integral 0 to x f of u z of x minus u d. So this is the convolution of two functions. Now we move on to the important property which is known as the convolution theorem for Laplace transformation. Convolution theorem for Laplace transform. First we write the statement of this convolution theorem. What is the statement of the convolution theorem? If Fp and Zp are Laplace transformation of fx and gx, that is, if Fp is the Laplace transformation of fx and Zp is the Laplace transformation of gx, or in other words, if we say that fx is the inverse Laplace transformation of Fp and gx is the inverse Laplace transformation of Zp, then then the inverse Laplace transformation of Fp into Gp with respect to x is equals to integral 0 to x f of u g of x minus u du, and the right hand side is nothing but the convolution of two functions f and g. So we have to prove that for convolution theorem, we have to prove that inverse Laplace transformation of Fp into Gp, that is the product of the two functions Fp into Gp, is equals to integral 0 to x f of u g of x minus u. So the proof of this theorem, we will use the properties of the Laplace transformation to prove this theorem. So in order to prove that inverse Laplace transformation of Fp into Gp is equals to integral 0 to x f of u g of x minus u, we have to prove here the Laplace transformation of integral 0 to x f of u g of x minus u du, Laplace transformation with respect to p. We have to prove that this is equals to Fp into g. So in order to prove this theorem, we have to prove that the Laplace transformation of this one, this is the convolution of two functions, this is equals to the product of Fp and Gp. So we proceed to prove this one. The left hand side we use the Laplace transformation of integral 0 to x f of u g of x minus u du with respect to p. By definition, this is equals to integral 0 to infinite e raised to minus px integral 0 to x f of u g of x minus u du dx. This is the limit of x, so x is equals to 0 to infinite, and this is the limit of u, so this is u is equals to 0 to x. So by using the definition of the Laplace transformation, we have to calculate this integral. Integral x is equals to 0 to infinite e raised to minus px, and the integral with respect to u is equals to 0 to x f of u g of x minus u du. Now in order to calculate this integral, first we change the order of integration. Changing the order of integration. Changing the order of integration. Here the limits are from u to x and x is equals to 0. The limits are from u to u is equals to 0 to u is equals to x, and x is equals to 0 to x is equals to infinite. So if we change the order of integration, if we take this is the axis of x and this is the axis of u, then first the limit of u is equals to 0, that is axis of x, and the limit u is equals to x, which is a line inclined with 45 degree. So this is u is equals to x, and the x is equals to 0. X is equals to 0 is the ux, axis of u, and x is equals to infinite towards the infinite. First, changing the order of integration, we have here u is equals to 0 to u is equals to x along the axis of u. Axis of u is equals to 0 to u is equals to x is this one. Now we have to change the order of integration. So take the limit first of x here. So the limits are from this one. So the limits of x, after changing the order of integration, if we change the order of integration, then we have the limits of x is equals to, we have the changing the limits we have the x is starting from this one, so this is x is equals to u, and towards the infinite, so x is equals to u to infinite, and the limit of u, the limit of e is starting from the 0 to the limit u. So this is u is towards infinite, so this is x u is equals to 0 to infinite. So after changing the order of integration, we here find that the Laplace transformation of integral 0 to x f of u z of x minus u du with respect to p is equals to, after changing the order of integration, here we first integrate with respect to u and then x. Now changing the integration, first we integrate with respect to x and then with respect to u. So this is integral, the limits of u are from 0 to infinite and the limits of x are from u to infinite. So the first, the limits of x, that is g of e raised to minus px, z of x minus u dx, then du, and outside the integral of x is f of u. So we change the order of integration. First, now we integrate with respect to x and then u. Now in the internal integral, if we put x minus u is equals to y, then we get this is equals to u is equals to 0 to infinite f of u. The internal integral is integral x is equals to 0. When we put x minus u is equals to y, then y is equals to 0 to infinite is the limit, e raised to minus p, x is u plus y, z of y dy, and then with respect to e. So calculating this integral u is equals to 0 to infinite, here by taking e raised to minus pu outside the integral, which is independent of y, so e raised to minus pu f of u, and inside the integral it is y is equals to 0 to infinite e raised to minus py z of y dy into d. The internal integral is nothing but the Laplace transformation of the function gy or gx, and the Laplace transformation of the function gx is taken as gp. So this is equals to integral u is equals to 0 to infinite e raised to minus pu f of u into gp. Now taking gp into du, taking gp outside the integral, we get gp into integral u is equals to 0 to infinite e raised to minus pu f of u. The integral is nothing but the Laplace transformation of the function fx, and the Laplace transformation of the function fx is fp. So we get this one as gp into fp, that is fp into g. So we have find the Laplace transformation of integral 0 to infinite f of u z of x minus u du is equals to fp into gp. So taking the inverse Laplace transformation, we get, this implies the inverse Laplace transformation of fp into gp with respect to x is equals to integral 0 to x f of u z of x minus u du, which is the required convolution theorem for Laplace transformation, which is the convolution theorem for Laplace This is a very important theorem for the Laplace transformation. It will be used to find various integrals of the convolution type. It is also used to solving the integral equations of the special type which are of the convolutions type. So thank you very much.